Welcome back to our OEIS deep dive, where we dig into those fascinating integer sequences from the online encyclopedia of integer sequences.
Always a pleasure to be back.
Yeah, as number theory students, we spend so much time looking at these sequences, and sometimes they feel kind of abstract. But, today I think we have a really interesting one.
Indeed.
A000163. These are called the series parallel numbers. And trust me, this one, it gets really concrete, even going into the world of electronics a little bit.
It's always exciting to see those connections between seemingly abstract mathematics and the real world.
Absolutely. So let's just jump right in. The first few terms of this sequence are 2, 8, 3, 4, 136, 538. And I'm going to ask you, what do these numbers actually represent?
Well, they represent the number of ways you can arrange resistors in a circuit using only series and parallel connections.
Okay, so I'm thinking a series connection would be like things in a line.
Exactly like a single pathway.
And a parallel connection would be like multiple paths?
Precisely. You can think of it like building a road network between two cities. Series connections are like a single highway, while parallel connections offer multiple routes.
Okay, so these numbers count all the possible road maps you could build with a given number of resistors.
That's a great analogy.
That's pretty cool, but I have to admit at first glance it doesn't seem that mind-blowing.
But that's where the series parallel element comes in. You see, the number of possible arrangements doesn't just grow linearly, it explodes.
This blows, whoa.
Adding even one more resistor drastically multiplies your options. That's why we need mathematical tools like generating functions to help us calculate these numbers, especially as the sequence progresses.
Generating functions, oh yeah, we've talked about those before on this series, but maybe you can remind us what those are and why they're so helpful in this case.
Sure, imagine trying to calculate the 100th term of this sequence directly. It would be a nightmare.
Yeah, it would be a huge calculation.
Exactly. Generating functions act like a shortcut. They encapsulate the entire sequence into a single function.
Like a master key that unlocks any term we want.
Precisely.
Okay, so instead of brute forcing our way through each and every configuration, we can use this master key and jump straight to the answer.
You got it.
That's incredibly efficient. But looking at the formula for A000163's generating function, it references another sequence, A000084. What's going on there?
That's where things get even more interesting. A000084 deals with partitions, the ways to break a number down into smaller parts.
Partitions.
For example, the number 5 can be partitioned as 1 plus 4, 2 plus 3, or just 5 itself.
Okay, so different ways to add up to that number.
Exactly, and in the context of our circuit analogy, think of each partition as representing a different way to arrange resistors in parallel branches.
Wait, I'm not sure I follow. Can we maybe unpack that a little bit?
Absolutely. Imagine each parallel branch in your circuit as a separate part of the partition. The number of resistors in each branch corresponds to the size of that part. So if you have 5 resistors and you want to arrange them in parallel, the partitions of 5 give you the different ways to split them up among those parallel branches.
Okay, I think I'm starting to see the connection. So by combining the concept of partitions with series connections, we arrive at this huge number of series parallel configurations captured by A000163.
Precisely.
It's fascinating how these seemingly disparate mathematical ideas intertwine like that.
It is indeed, and that interconnectedness is one of the most beautiful aspects of mathematics. The OEIS helps us see these hidden relationships between sequences and concepts.
Yeah, and it might seem at first like, oh, this is just some abstract sequence. Yeah. But I have a feeling this has some real-world implications.
Oh, absolutely. It goes far beyond just circuits.
Okay, I'm excited to hear more about that.
You're absolutely right. It goes way beyond just circuits. The applications of series parallel numbers are surprisingly diverse. Remember, at its core, this sequence is about quantifying complexity.
Okay.
It's about understanding how quickly the number of possibilities explodes when you combine simple elements in different ways.
So where else does this kind of complexity come into play?
Well, let's start with something seemingly unrelated to circuits biology. Think about the circulatory system.
Okay, yeah.
We have arteries branching into smaller vessels, eventually reaching capillaries, then converging back into veins.
Right.
That intricate network, it's crucial for distributing blood throughout the body, and it exhibits both series and parallel arrangements.
So are you saying that the same math we use to analyze circuits could be applied to understand blood flow in the human body?
Precisely by analyzing the series and parallel connections within the circulatory system, we can gain insights into blood pressure, oxygen flow, and the efficiency of nutrient delivery. Medical researchers can even use these principles to model the impact of blockages or abnormalities in blood vessels.
Wow, that's incredible. It's
Yeah.
amazing to see how a concept that originated in electrical engineering can have such profound implications for understanding the human body. But I'm guessing biology isn't the only unexpected application here.
Not at all. Consider social networks, for example, how information spreads, how communities form, how influence propagates. These are all processes that involve connections, much like our resistors in a circuit.
Okay, but social networks seem a lot more fluid and dynamic than electrical circuits. How can we apply the same rigid mathematical framework to something so complex and constantly changing?
That's a great question. While social networks are indeed dynamic, the underlying principles of connectivity still hold true. Think about how you might share a news article online. You might post it to your own profile, which would be like a series connection reaching only your immediate followers.
Right.
But then those followers might reshare it with their own networks, creating a cascade of parallel connections that amplify the reach of the information.
So analyzing this series and parallel connections within a social network can help us understand how information goes viral?
Exactly. And it goes beyond just viral content. By studying these patterns, we can gain insights into how opinions form, how social movements gain momentum, even how marketing campaigns effectively target specific audiences.
This is blowing my mind. It seems like series parallel numbers are a hidden key to understanding the complexity, not just of physical systems, but of human interactions as well. But before we move on, I want to go back to that generating function. We talked about how it acts like a shortcut, but can you walk me through how it actually works in this specific case?
Of course, remember the generating function for A000163, which is 21 plus S1S3. It relies on the generating function for A000084, which deals with partitions by plugging in the generating function for A00000804, which is a bit more complex.
Mhm.
We can manipulate this formula to extract the coefficients. Each coefficient corresponds to a specific term in this series parallel sequence.
So it's like a nested formula. We use the generating function for partitions as an ingredient in the generating function for series parallel numbers.
Precisely, and this highlights the beauty of generating functions. They allow us to encode complex relationships between sequences into concise mathematical expressions. It's like having a powerful tool that lets us navigate the intricate web of mathematical patterns with elegance and efficiency.
Okay, that makes more sense. Now, it's amazing how mathematicians develop these tools to grapple with such complex concepts. But I have to ask, even with these tools, was it challenging to calculate the first 500 terms of A000063?
It certainly wasn't a trivial task. Shanae Irvine, who extended the sequence to 500 terms, deserves a lot of credit. It required sophisticated algorithms and computational power to handle the sheer number of possibilities as the sequence progresses.
It makes you appreciate the dedication and ingenuity of mathematicians who push the boundaries of our knowledge. But I'm curious, even with 500 terms calculated, are there still unanswered questions about this sequence?
Absolutely. One of the most intriguing open questions is whether there's a simpler, more elegant formula for calculating these numbers directly without relying on generating functions, or recursion. Finding such a formula would be a major breakthrough.
So even a sequence as seemingly well understood as A000163 still holds mysteries waiting to be unraveled. That's inspiring. It reminds me that there's always more to discover in the world of mathematics.
Precisely, the OEIS is a testament to that spirit of exploration and discovery. It's a vast and ever-growing collection of mathematical treasures, each sequence with its own unique story to tell.
It's incredible to think about how those first few terms, 2, 8, 34, 136, 538, they each encapsulate this vast network of possibilities.
It is quite remarkable.
It's like each number is like a little seed, and then it sprouts this intricate mathematical structure.
That's a beautiful analogy, and it really highlights how the OEIS isn't just a collection of numbers, it's a portal to entire universes of mathematical concepts.
Yeah, and we started with this seemingly simple idea of like arranging resistors, and then all of a sudden we're talking about blood vessels and social networks and like the fundamental nature of complexity.
Indeed, that's the power of abstract thinking. It allows us to develop tools and frameworks that can be applied across so many different fields.
So for our fellow number theory students out there listening, what's the big takeaway here? What makes this sequence A00000163 worth remembering?
I think it's a reminder that even the most abstract mathematical ideas can have surprising and profound connections to the real world. Don't underestimate the power of curiosity and exploration. You never know where a simple sequence of numbers might lead you.
It's like that saying, it's all connected. We just might not see those connections at first glance.
Precisely. And for anyone who's intrigued by this sequence, I encourage you to explore the OEIS entry further. There's a wealth of information there, from mathematical formulas to links to related sequences and research papers.
Yeah, and who knows, maybe one of you listening will be the one to discover that elusive, elegant formula for A000163.
It's certainly possible there are still mathematical mysteries waiting to be solved.
Well, on that note, we'll wrap up this deep dive into the fascinating world of series parallel numbers.
It's been a pleasure.
Thanks for joining us, and we hope you've enjoyed exploring this sequence with us and that it's sparked your curiosity to, you know, delve deeper into the OEIS and all the wonders it holds.
Until next time, keep exploring, keep questioning, and keep those number-loving minds engaged.